right. Yeah, I think it'll be reasonable to start here. So, yeah, welcome to session 9A, which is Tools and Datasets Part 3. So, yeah, thanks for all your attendance so far, and also for coming to this session. Please do remember there is the chat that is associated with the Zoom is not going to be in effect. You can instead enter questions that you have on the Slack channel under the 08 Tools and Datasets within that channel. And then if there is some time at the end of a given talk, I'll maybe read through a session or read through a question, and the speaker can give an answer. Otherwise, there is also a Q&A session at the end. And I would also ask that the speakers at some point also go through the list of questions on the Slack channel, especially if the questions that we do not get to during the session, and then you can answer them and have any kind of follow-up discussions that you see fit. So yeah, I guess we can first start with Alex Belochitski, who will talk about neural network emulators.
Hi, can you see my screen?
Yes.
Excellent.
Thank you.
So my name is Alex Belochitski, and I'm going to talk about the work Vladimir Krasnopolsky and myself have done on building a stable, accurate, and fast neural network-based emulator of the entire suite of model physics in a state-of-the-art atmospheric general circulation model. As many or most of you know, atmospheric models consist of a solver of fluid dynamics equations that are usually discretized in case of global models on the entire globe. But the models that are currently used in operations use comparatively coarse resolutions of a few tens of kilometers. As a result, many physical processes are not resolved in such a model, and they need to be parameterized. In case of global atmospheric models, these processes have to do with clouds or subgrid scale turbulence or radiative transfer. And oftentimes, such components of the global atmospheric models take up substantial part of model integration time. And previously, a number of attempts have been made to emulate some parts of the suite of physical parameterizations in atmospheric models. For example, radiative transfer parameterizations or gravity wave drag were emulated successfully. So what we are going to present here is an emulator that encompasses the entire suite of physical parameterization in a GCEm. And here on the left-hand side is a rectangle that lists all of the parameterizations that are used in this model. It's radiative transfer, microphysics, boundary layer, gravity wave drag, shallow deep convection, effects of CO2 and trace cases, and also a land model. So our goal here is to replace all of this with a single neural network. The reason why this might work is that if you were to look at individual tendencies produced, or rather the tendencies produced by individual parameterizations in this suite of parameterizations, you will find that they're fairly complex and highly nonlinear. However, when all of them are taken together, quite a few of them are compensate for each other. So the resulting diabatic tendency from the entire suite is usually smoother than what you would get from an individual parameterization. So we are going to configure our global atmospheric model here to have a 100 kilometer resolution in the horizontal and 64 layers in the vertical. This corresponds well to the current to the spatio-temporal resolution of current generation of climate models, and it will also help us to generate and handle fewer data than we would have to deal with in case of a high resolution model. We will also replace a couple of parameterizations with somewhat simpler versions of the same of parameterizations present in this process. For example, we'll replace microphysics parameterization, which predicts 5 microphysical species, with a parameterization that uses only 1 total cloud condensate. And we will replace the boundary layer scheme, which uses prognostic TKE, turbulent kinetic energy, with something simpler. But having said all this, these parameterizations that we're going to use in our setup correspond well to what is used in current generation of climate models. But the main goal of this is to almost half the number of prognostic variables in the model. And we're also going to, because the full suite of atmospheric physics encompasses both radiation and atmospheric physics block, and because it's invoked with the frequency of the physics block, we configure the model to follow radiation with each physics time step for the sake of consistency between experimental and control configurations. Here's how we design a training set. The data. Here's how we generate data for our emulator, and what exactly is going to be saved, I will discuss in a moment. We run 24 10-day forecasts initialized at 0Z on the 1st and 15th of each month of 2018, and we save instantaneous data 3 hourly. This way we capture diurnal and seasonal cycles. And from each 3-hourly global snapshot, we randomly select 1,500 profiles. And as a result, we use in our training process only about 3% of the entirety of the data that we saved. Now, our emulator is a shallow neural network, which has 75 neurons in a single hidden layer. And it has 186 inputs, and I will talk about what these inputs are in a moment, and 304 outputs. And once again, I'll discuss it in a moment. This emulator is 20 times as fast as the original physics block that calls radiative transfer on each physics time step, and 4.5 times as fast as the original block, which calls radiative transfer hourly. Now, the way we're going to evaluate this emulator is as follows. I'm not going to show any offline results, but instead, I'm going to show the results from the online simulations, where we put in our emulator into the global model and ran forecasts with it. So we will perform 24 10 days forecasts, once again initialized at 0Z on the 1st and 15th of each month of a different year. So we generate the data for training in 2018, and we will run our forecast in 2017. So it will be tested on the data that is not present in the training data set. And we're not trying to improve on the forecast here, but we're trying to emulate exactly what the model is doing. So here's a somewhat busy table that shows inputs and outputs of our emulator. And I would like to draw your attention to the lower part of the table, which shows outputs of the emulator. And each of these outputs consist of 6 vertical profiles, each having 64 elements in it, corresponding to 64 vertical layers of the model. And these profiles are increments of components of the wind, of temperature, specific humidity, cloud condensate, and ozone. So these are prognostic variables of our global model. And our emulator will calculate these increments and supply them to the dynamical core that solves fluid dynamics equations. The inputs are, we have somewhat larger number of inputs here. Well, first off, of course, we supply profiles of the same prognostic variables that we receive from the dynamical core, the winds, the vertical velocity, the temperature, but also we do a couple of additional things here. First, we sample our profiles in the vertical because these profiles are highly correlated in the vertical, and some of them contain, some of them are either almost zeros. On some layers, for example, ozone in this model in the troposphere is practically non-existent. Or once again, in this model, specific humidity is practically zero in the stratosphere. So we don't include information about those layers. But knowing the state of the atmosphere is not enough. It's also important to know where the planet is located in the orbit and what time of day it is. So that's why we supply the model with the information about current months and current day, location of a given column. Oh, I forgot to mention that the emulator acts in a single column of the model. So we supply the emulator with information about the location of that column of the globe and the cosine of the zenith angle. Well, first, I'm going to show you some sanity checks. First, so we ran 24 10-day forecasts in 2017, and this is the zonal and temporal average over the variables that the emulator is predicting. So UV temperature are shown on this slide. So the column on the left-hand side, the upper panel shows U component of wind generated by the neural network. The middle panel shows the same for the control run, and the lower panel shows the difference. So we can see that the neural network captures the for example, jet streams pretty well, and the globally averaged differences or bias for U is about 0.1% of the average value of the wind. The same can be said about zonal temporal averages of V component of the wind. For example, here the neural network shows lower branches of the Hadley cell and lower branches of the Ferrel cell and upper branches of the Hadley cell, and same goes for the control run, and the differences once again are on the order of 0.1%. And once again, we see that the neural network captures warm temperatures in the tropical belt and very cold tropical tropopause. In other words, and the differences are also on the order of 0.1%. In other words, the forecasts, our forecasts, when looked at in this manner, definitely appear like planet Earth. And I'm not going to concentrate too much on this slide, but this shows the same temporal and zonal averages for specific humidity, cloud condensate, and ozone, and the same conclusions hold for these variables. Everything looks very much like planet Earth, and all forecasts, I forgot to mention, are stable. So, but our goal is to use this emulator in a weather forecasting model. And of course, what this kind of performance, online performance of the emulator is still not good enough. We have to make sure that the temporal evolution of our forecast is also of good quality. So I'm going to show some forecast verification scores that we calculated for our emulator. And for those who are maybe not exactly familiar with what they are, we're going to calculate anomaly correlation coefficient, and here a forecast is verified against analysis, so which is labeled as A in this formula. And anomaly is calculated against climatological means. The reason for that is that we don't remove climatology, then the correlation coefficient is always going to be close to zero. It's not going to be very informative. So we calculate, and then we calculate correlation for those anomalies. So we calculate anomaly correlation coefficients for both our experimental run that uses the neural network and the original model that uses the physically based parameterization package. And we're also going to look at the root mean square error, which is going to be calculated against analysis for both experiments. Here I'm showing anomaly correlation and root mean square error of 500 hectopascal geopotential height. And once again, this is an average of a 10-day forecast spanning 2017. The reason we look at hectopascal height is that pressure on this level in the atmosphere determines evolution of mid-latitude synoptic systems. So forecasters all pay close attention to how well this quantity is predicted. So the upper row shows anomaly correlation scores, and the lower row shows root-mean square errors. And the columns show the scores for northern hemisphere, southern hemisphere, and the tropics. Now let's concentrate on the upper left panel. The upper part of the panel shows anomaly correlation scores calculated both for the control, shown in black, and the experiment with the neural network, shown in red. And the lower panel shows the difference between these two curves. Now, the vertical rectangles show on the difference panel mean that if the difference lies within these rectangles, or rather, if it lies outside these rectangles, then the difference is significant within the 95% confidence levels. So our goal is to make sure that the difference lay within these vertical bars. And if you look at the anomaly correlation scores for 500 hectopascal height, you will see the differences are not only small, but they're not statistically significant for either of the hemispheres or for the tropics. The panels for root-mean square errors show very similar results. The differences between root-mean square error in the two rounds is not statistically significant, this is a very encouraging sign. This slide shows anomaly correlation and root-mean square error for 800 hectopascal temperature. And this is the level just above the boundary layer, and it's used. Weather forecasters use this level for looking at warm and cold fronts. Once again, the same conclusion holds for this for these variables. The difference between the forecast, the control run, and the experiment is not statistically significant, except you may notice that there is some statistically significant difference in the beginning of the run for northern hemisphere. And this is caused by technical issues, because the data at forecast hour 0 is actually saved after the first model time step, and what we're seeing here are the effects of the model spin-up, and we see that. But having said that, this difference is very small. This is 1/1000th of the unit of anomaly correlation scores, and when we get to the next data point at 24 hours, we're already within the range of the difference of not having any statistical significance. And finally, these are the anomaly correlation scores and root-mean square errors for zonal velocity at 200 to 250 hectopascal height. This is the location of the jet stream. And in general, the same conclusion holds. There is no statistically significant difference between the forecast generated using the neural network and the original model. So does it mean that there are no issues with the emulator performance whatsoever? Not entirely. There are some statistically significant temperature biases in the upper stratosphere at 10 hectopascal and above. And here's an example of plots that show such biases. But and you see the difference lies outside of the statistical significance zone. But these differences are small, and we suspect that they may have something to do with our aggressive sampling of the temperature profiles for preparation of our training data. But otherwise, the emulator is accurate, fast, and stable, and it performs very well on out-of-sample data in the online mode in 10-day forecasts. There are much more verification plots of this nature that you can look at, and I will put this link here at the bottom of the slide in the Slack channel so that those who are interested can take a look at it.
Oh, now you have about 2 minutes. Thank you.
Thank you. This is the last slide. So what can this be used for? As you remember, the outputs of the emulator are just these 6 vertical profiles that are supplied to the dynamical core. The emulator does not generate any of the diagnostics that is expected from a global model. For example, it doesn't generate BBL height. So what can it be used for? Well, one idea is that in the NCEP, the operational ensemble data assimilation system, launches 80 short-range ensemble members each cycle. And they're used for estimation of flow-dependent uncertainty of the forecast. And they supply only the final atmospheric state, these six vertical profiles that our emulator generates. And no calculation of diagnostics is performed. So we can use this emulator for acceleration of the data assimilation ensemble. But another, in my opinion, more appealing idea is to use this emulator in 4D data simulation that requires tangent linear and adjoint models for the physics package. So the shallow neural networks are trivial to differentiate analytically, and using training coefficients of the original neural network in the NN Jacobian will result in a tangent linear model. And transpose of the results in matrix will yield an adjoint. This approach has been successfully tested at ECMWF recently, using an emulator of orographic gravity wave parameterization in their 4D system. And this is all I have. I'm going to stop here.
Hey, thank you so much for that, Alex. Yeah, please don't. We won't be able to get to this right now, but there is a question already in the Slack channel, and so please feel free to add questions to the Slack channel. And tag it with the @ symbol and the speaker's name as has been done for this one question. So thank you. Okay, we have Huang talking to us about spatio-temporal neural networks.
Okay, everybody see the slide?
Yes, there it is. Thank you.
Okay, good morning. I'm Huang, and I'm a PhD student from Florida Atlantic University. And I'm presenting our research group to present our preliminary work on the loop current system prediction. And it's called a 3D STN, a spatial-temporal neural network for the long-term volumetric velocity forecasting of the loop current system. So first, what is the loop current system? So the loop current system is also called Florida current. It is an area that the warm water flows through the Caribbean and pass through the Ucayali Peninsula and into the Gulf of Mexico. And this forms the Gulf loop current, in which curved east to the Florida coast and extends through the Straits of the Florida. And understanding the dynamics of the loop current system is very fundamental to understanding the Gulf of Mexico for oceanographic systems and vice versa. The accident and activity like the hurricane intensity, offshore safety, and something like the oil spill responses and the Gulf Coast economy are all affected by the position, the strength, and the structure of the loop current systems. And here, despite there is a major impact of the loop current system on human and the natural systems, the knowledge about the underlying dynamics that controls its behavior is limited. The loop current is one of the fastest current in the Atlantic. It's traveling at speed of approximately like 0.8 meters per second, and it's typically about 800 meters deep. However, the dynamics of current and its eddy sheds, like here, are not well understood. The loop current position varies greatly from its retracted days to the extended days into the far northern and the western Gulf. So why and when the loop current suddenly intrudes north has not been be able to be predicted with sufficient skill. And occasionally the eddies shed from the loop current and slowly migrate westernwards, beginning with its loop currents, warm water, and strong currents. So what triggers that separation when and when it happens are also not very skillfully predicted. Therefore, the National Academies of the Science, Engineering, and Medicine published the report that calling for the development of the predictive models that are capable of forecasting the current speed, the vertical structure, and the duration of the loop current. And it added a week ahead, and also the loop current propagation a month ahead, and also the eddy shedding events up to 16 weeks ahead. So in this work, we explore the third case to predict the current speed and its vertical structures. To understanding the loop current, the committee's overarching recommendation is to create a comprehensive and long-term vertically integrated set of observations over the loop current's active area. So especially the relevant areas indicated in the purple zone. The dataset used in this study was produced by a funded observational program called the Dynamics of the Loop Current in U.S. Water Studies by Hamilton. So this observational program consists of a high-density area of 125 moored instruments over a 2.5-year period, which beginning in the April 2009. The U.S. mapping area was located to cover both the east and the west sides of an extended loop current between the West Florida slope and the Mississippi Sand. It was also centered over the zone where the separations of the loop current eddies from and the loop current were most likely to occur. And in these figures, we show the location of the moorings and the pressure-equipped inverted echo sounders, just for the pies, deployed in the U.S. and Mexican sectors in the eastern Gulf of Mexico during the study of the loop current dynamic. So the thick purple line shows the mean boundary of the loop current, and from the June 2009 to the June 2011 interval. So in this study, we utilized a time series which was processed with a fourth order Butterworth filter and subsampled at 12 hours intervals. So consequently, the total dataset contains a total 1810 records, which means like 905 days. So at each top step, as shown in this figure, we only plot the first 30 layers, which cover the range of 5-meter depth, and we show the 5 layers in this plot. So the data were formatted as a continuous sequence of 3D clips, where each dimension of the data represents the depth, the longitude, latitude, and channels. And the channel stands for the geotropic velocity vector in the U and V components. So the challenge. So the loop current prediction can be regarded as a spatio-temporal modeling problem. So take the information propagation mechanism of the dynamic system as an example. As shown in this figure, each node represents a geographic location observing ocean currents, And the node can be also considered as an observation point of a 2D or 3D object we are modeling. So there are three types of dependencies exist in the spatial-temporal modeling. The first one is called the spatial dependence, which means that a node in the grid concurrently affects and be affected by its neighbors. And the second dependency is called the temporal dependency, which means a node's data depends on its previous data and affects its future data. And the third one is a spatial temporal dependency, which means a node even directly influences its neighbors nodes across the time steps. So to deal with that, those challenges above, we introduced a simple spatial temporal neural network to focus the loop currents. So the focusing model is applied to all the nodes of the mesh or grid, so which means we apply the same operation to generate dynamic predictions at different spatial locations in the grid. So the focusing model encodes mesh nodes by using recurrent neural network LSTM to model and predict the spatial temporal time series dynamics. So the focusing model consists of three parts: an input linear layer that for the information fusion, and the LSTM layer and the output linear layer. So it receives three different kinds of information. The first one is the dynamics input, which is a variable that we're predicting and learning that changes over time. And the second one is the lateral information. The lateral information is the information that's from the neighboring nodes. And the third one is the position info. The position info is a constant embedding, and it characterizes the location of the each node. So as shown in the figure, the green node is where we are applying the focusing nodes now, and it integrates the values from its 6 neighboring nodes to produce the prediction at the next time step. So in order to let the model to make use of the position info, we must inject some information about the relative or absolute position of the node in a mesh or a grid. So to this end, we add the positional encoding at the position info to the input embedding. This method is—
You have 2 minutes.
Okay, this method is inspired by the transformer, which uses sine and cosine pairs to indicate the relative absolute position of the tokens in the 1D sequence. But in this work, we extended into the 3D manners. So we choose the function because we hypothesized that it would allow the model to easily learn to attain the relative and absolute position in the grid. So, and this method has been validated in the transformer model. So the focusing model is a simple neural network, and it's applied to all nodes of mesh, which means the model can be applied to any position we're interested in. And thus it's scalable to different size and shape of the mesh. This model is simple, and thus it is critically less prone to be overfitting. And it's predisposed to identify the universal recurrent pattern dynamics. As for a physical system, there are some predictable patterns will be repeatedly happen at different spatial locations. And since we're applying the same model to different locations, it's more likely to capture the repeated patterns. And here is the result of our model and the performance. We trained out our model with 100 days of historic data and predict the next 3 weeks. So each time step means 12 hours, which means half days. And our model yields a small test error over long horizons, which is much harder than just a single time step ahead prediction. And in our ongoing study, we are particularly interested in whether the model can be performed well in the whole Gulf of Mexico loop current prediction. and compared to the climate forecasting, where the changing in the loop current is much slower, but the changing in the climate forecasting is much faster, and we will investigate in whether it will be robust in the faster changing climate forecasting. And here are some of the citations in our other work. Use the physics-informed neural network for the dynamical system prediction. And thank you.
And thank you. Please do put questions for you, Huang, in the Slack channel, as Chris Slocum has given the channel name there. So thank you. And next we have Julien Brajard on super resolution data assimilation.
Yes, thank you very much. We'll just start the slideshow. Okay. Yes. Good morning, I guess, everyone. So my name is Julien Brajard. I will present the work we have done together with Sébastien Barthélémy at the NOAA Center, NERSC, in Bergen in Norway. Yes. So quickly, yes, the objective of the work. So data assimilation, the aim of data assimilation is to estimate the state of a dynamical system, for example, the temperature, the pressure of an atmospheric or oceanic system, given the forecast of the numerical model, and correcting this forecast using observation. But in a lot of cases, you have that the resolution of the observation, they are smaller and they are better than the resolution of the model, because having a high resolution model, as you very well know, is very costly. So the objective of this work is to show how we can assimilate a high resolution observation, but still with using a low resolution model. So I will try to introduce the motivation and also the method we have applied, which I think it's the basic idea is quite simple. So how does the data assimilation works, and more precisely, how does an ensemble data assimilation scheme works? So you have some initial conditions that can be obtained by a previous data assimilation step, for example. So in that case, you have initial conditions that are in a low resolution. So from those initial conditions, you run your numerical model in low resolution to produce some low resolution forecast. And then you try to integrate some high resolution observation, denoted Y here, into the DA system to correct the forecast and to produce an analysis or a corrected state. So of course, if I try to summarize the pro and the cons of this process, as you assimilate high resolution observation in a low resolution state, all the high resolution scale of the observation will be considered as noise by the system. So you will have a high observation error. And also, as a consequence of the low resolution model, you have some high resolution processes that are poorly resolved by the model, or maybe not resolved at all. But as you have a low resolution model, your computation cost is relatively low, and you can afford to have big ensembles to propagate in time big ensembles. So the other side of the coin is to have a high resolution model. With a high resolution model, you have a high resolution initial condition. So the principle is exactly the same. But as you have the forecast, which is in high resolution, you have a low observation error. And of course, your model being in high resolution, it will better resolve all the high resolution processes. But of course, there's no free lunch. So if you do that, you will have a higher computational cost, and one of consequences might be that you cannot afford to have a big ensemble forecast. You have maybe one or two members in your ensemble only. So the idea we have is to combine both of these worlds, if I would say. So we will use a low resolution model because it's cheap, and we produce so a low resolution forecast. But before doing the data assimilation step, what we are doing is we do a super resolution, so a downscaling operator, to produce a forecast in high resolution. And then we do the data assimilation in high resolution. And then if we want to propagate our analysis or corrected state once again in a low resolution model, we need just to upscale the high resolution analysis. So if we do that, of course, we have a low observation error because the DA step is done in a high resolution space. you may hope to resolve better the high resolution processes in the model, but still your computational cost is low and you can afford big ensemble. So this is basically the idea. So we have applied this idea to a quasi-geostrophic model. So we have used a high resolution model to produce our observation, and we will test the idea with two different configurations. One with a low resolution model, which is divided by 2, the size of the grid size, and an ultra low resolution model, so even more degraded low resolution model. So we'll try to run those two low resolution and ultra low resolution models to assimilate observations that are in high resolution. So we need first to learn a downscaling operator. So we'll use two downscaling operators, one very simple one, which is basically cubic spline interpolation, and one more elaborated, which is a neural net. So to train the neural net, we have used one simulation of a high resolution model. And from sample of the high resolution model, we have propagated in time from one time step the high resolution model and with the low resolution model. So we have two samples that can be compared, one high resolution sample and one low resolution samples. And we try to learn the mapping between those low resolution and this high resolution. So to infer the high resolution from the low resolution. This is a very standard super resolution approach. We have done the training with 8,000 such samples, and we have validated the process with 2,000 samples. And this is the example of what we obtained for one sample in the validation set. So here you have the reconstructed field from the low resolution state or the ultra low resolution state, both for the neural net and the interpolation. So if you look at the raw state, you see mostly no difference. But if you look at the error, you see there that some very contrasted results. So two comments. First, you see that for each resolution, the neural net performs better than the low resolution, the interpolation. And of course, as expected, it's more challenging to reproduce high resolution from an ultra low resolution state than for only a low resolution state. But still, the error is still low with the neural net from the ultra low resolution state. Even more interesting, maybe, if you look at the model, you see that there is some ADs that propagating westward and eastward. So if you do a section here, and if you look at the evolution of this AD on this section, so you see that in time the AD go first westward and eastward and westward. And if you look at on two particular time, if you look at the error of the reconstruction by the neural net and by the interpolation, you see that it's quite flat for the neural net, but in the interpolation you have this like bimodal shape, which means that actually there is an error in the position of the ADs. And what does it mean? It means that when you interpolate basically the low resolution model, and it means that the AD is not well positioned. So it means that there is some error in the motion, the representation of the motion of the AD. And so the result here is that the neural net is able to correct the displacement error, so the error in the representation of the AD. Basically, in the low resolution models, the AD are moving too slow. And this is corrected by the neural net. And this is corrected when the AD are moving eastward or westward. So the neural net has learned, in some extent, the model error, the low resolution model error, and correct the low resolution model error. So here are the results for the assimilation itself, with low resolution and with ultra low resolution model. So the black line is the root mean square error with the low resolution data assimilation. So everything is done in low resolution. And the red line is the same thing for high resolution. So you do everything, including the model in high resolution. But this is very costly because you need, for the red line, you need to have a high resolution simulation, a high resolution model. For the green and the blue line, this is a result for the super resolution data assimilation, with the green line with the neural net downscaling and the blue line only the interpolation. And you see that with the green line, so with the neural net downscaling, you perform, the method is performing almost as well or similarly to the high resolution. It's a bit less true for the ultra low resolution model, but still this is quite correct. You have to remember that to have the green error here, you only need to run the ultra low resolution model. So it's very cheaper than obtaining the DA in high resolution. Okay. If you reformulate a bit the Kalman gain operation, so I won't make the math here on the presentation, you can separate basically the correction which is due to the model error correction. So this is what I have shown to you with the AD displacement, and the correction which is due to only the resolution error. And you see that mostly the error due to resolution error is quite stable in the time, but the error of model correction can improve a lot. The correction of the model error can improve a lot the restitution for very challenging events. So meaning when the model is performing very bad, the low resolution model, it can be corrected by the neural net. And now if we look at the cost, so you see that of course the cost of running the data assimilation in high resolution is very high. So you reduce a lot the cost if you run in low resolution or even ultra low resolution. The cost is a bit higher, of course, because you need to, for the super resolution data assimilation, because you need to add a down scanning step, which is a bit costly, but not too much. But what you gain a lot in cost, and you also gain with that super resolution data assimilation, a lot in error. If you look at the right panel here, you have the error of the restitution. So you see that basically the error of the neural net is very similar to the error of the high resolution data assimilation.
Oh, Julien, you have about 2 minutes.
That's great because I'm about to conclude. So yeah. So if I want to conclude on that, so I have shown that a scheme that mix standard data assimilation process with a super resolution done by neural net is able to reconstruct accurate analysis and close to what you would have with purely high resolution model. The neural net is even capable to correct model errors such as AD propagation, which is purely due to low resolution model. I didn't highlight that, but you have seen that the result was stable in time. And also I didn't show, but if you look at the ensemble itself, you see that the spread of the ensemble is represent well the uncertainty. So you have also a good reliability of the ensemble. So there is perspective of this work. Of course, we'd like to apply that to a more realistic model and especially with multivariate. And also, which is quite appealing with this method, is that you can apply this method only locally when it's useful. When you have high resolution features, you apply the downscaling operator. If you are in a region where there is less AD activity, for example, you can just use the low resolution data assimilation, and you gain even more computational cost if you do that. And you can also use the analysis produced in high resolution to initiate a forecast in high resolution. So we have a paper on that, but for some reason it's still on hold on the archive, so I cannot give you the archive link. But if you're interested in those results and the full results with the full paper, you can send me an email or to Sébastien, and we will give you the full details of this work. Thank you for your attention. Of course, I will stay here and
for the talk.
Sorry?
Oh no, and thank you for the talk.
Thanks for having me.
Yeah. So yeah, we have now we have Duncan talking about model calibration.
That's right. Good afternoon, good morning, everyone. Today, yeah, I'm going to talk about a package I've developed here in Oxford I'm calling ESM, and how I'm going to discuss a little bit about how we've been using that to calibrate models and explore uncertainty amongst different climate models. So many of you will be familiar with one of the core components of CMIP6 is the scenario MIP endeavor, and that asks multiple different models from around the world to project future climate change under variety of different socioeconomic pathways, so assuming different mitigation strategies and exploring what the climate impact of that of those different choices are. Now, as with any projection or forecast, there are uncertainties associated with these projections, and if you break these down into three kind of core components, so the variance, so the natural variability in the climate system, as a kind of fraction of the total uncertainty in temperature in this case, that reduces quite rapidly over time. So near term, the natural variability causes a large difference, a large part of the uncertainty in these projections, but that diminishes quite rapidly. The model uncertainty actually dominates over kind of medium short-term timescales, so 2040, 2050, which are very important for particularly high ambition scenarios. And as you go out to longer timescales than the scenario uncertainty, so the fact that we don't know, which of these pathways we're actually on, that starts to dominate. Now, this is kind of fairly intuitive, I think, and many of us might sketch something out like this when thinking about these different uncertainties. But if you look at other variables, so in my research, I'm particularly interested in the effect of aerosol on the climate system. If we just take one fairly common metric that measures the amount of aerosol in the atmosphere, actually model uncertainty contributes a significant fraction of the total uncertainty all the way out to 2100. So there are a range of uncertainties in these projections, and we might want to either try and reduce them, particularly in the case of model uncertainties. We want to be able to improve our models and reduce these uncertainties. And in the case of scenario uncertainty, we may want to explore those uncertainties and aid policymakers and the people who run integrated assessment models, for instance, to explore these various different pathways. So that's where this tool hopefully can help. ESM, so our system emulator, is a framework for taking model data, easily training different emulators on that data, allowing straightforward validation of those emulators, and crucially performing efficient inference using those emulators. And I'll explain a little bit what I mean by that on the next slide. But this kind of tool you can think of as a framework, really. So, the emulation actually is done by Keras or by GP flow if you're using Gaussian processes, but we wanted to create a straightforward, lightweight framework in order to enable scientists like yourselves to be able to pick up these tools and use them straightforwardly, swap in different emulators depending on what you're interested in, what's working well, or other people might have used in their research, and then perform inference on that. This is linked to a previous tool I've developed, Community Comparison Suite, which makes it easy to bring model data onto the spatio-temporal sampling of your observations. So it might be that your observations are satellite-based or ground stations, and those tend to be quite sparse spatio-temporally. And so this package allows you to easily bring the model data grid points onto this sampling, and then kind of perform this workflow. This also interfaces with the IRIS package from the Met Office and also X-Array. So you can bring in your X-Array data, perform emulation over that, and easily plot that using the X-Array interface. So one particular kind of use case, if you like, that I'm going to discuss using this package is exploring one particular type of model uncertainty, which is the parametric uncertainty in the models. So these big climate models have a number of input parameters, some of which are physical parameters that we understand and nevertheless have to tune somewhat within the model, and some of them might be unphysical. They might just be scalings on processes which we are inherently uncertain. Now, if you permit me to be a little bit abstract for a moment, if we think of a climate model as some super complex function f that nevertheless just takes some input parameters, such as the ones I described, plus emissions and concentrations and whatever, and outputs some large vector of outputs y. What I want to be able to do to estimate these parameters is do the inverse, right? I want to be able to take a set of observations of y, so y(o), and find what parameters allow the model to best match those observations. Now, this in practice is not well defined, and so we want to do this in a probabilistic way, and we defer to Bayes, and the want to seek the posterior distribution. So we set out to find the probability of a set of parameters given our observations, and that is determined by this likelihood, the probability of the observations given parameters times our prior of the parameters, and we have a normalizing value down here as well. So the difficulty in doing this is the fact that we don't have direct access to this likelihood. So we defer to a process called likelihood-free inference, sometimes called approximate Bayesian computation or rejection sampling. And the basic principle there is that we draw samples of parameters from our prior, the p theta, and calculate the forward model to determine y, and then accept that set of parameters that we got if given some distance metric, our output is close enough to our observations. So if rho here is some distance function and epsilon is some tolerance, if you like. And if this is close enough, then we accept theta. And it can be shown that if epsilon is large, then you can see that we will just end up accepting all of these theta, and our posterior will be equal to the prior. But as epsilon goes towards 0, it can be shown that this process generates observations from the posterior, which is exactly what we're after. Now, in practice, we need to do this tens of thousands, hundreds of thousands of times in order to densely sample our posterior. And so being able to calculate this forward operator using the climate model is impractical, right? We just can't run the climate model that many times. And so we use an emulator or a surrogate model that's sometimes referred to as to approximate this forward step. And then we can just do this ABC and approximate our posterior. So really, in this case, I'll just go back. So yes, so in this case, we're using the emulator to allow us to perform this inference. Now, a concrete example of that is this perturbed parameter ensemble, which we developed using one of our climate models to explore uncertainty in absorbing aerosol. So 2 of the 3 parameters we explored are the amount of absorbing aerosol that are emitted. We just scaled that up and down a bit. We scaled the absorptivity of the absorbing aerosols, so the imaginary part of the refractive index. And the output y that we're looking to constrain against is the absorption aerosol optical depth. And the emulator essentially allows us to fit through, performs a fit through this sparsely sampled space. So we have about 30 odd climate simulations that we then fit an emulator across. This is just a crude linear representation, just so you get the idea. And nevertheless allows us then to draw samples from this space very efficiently and determine the best combination of these parameters that match our observations of AAOD. So this output may not be a single value. This could be multi-valued. And so here I show a map of AAOD from the climate model itself and from 2 different emulators using parameters that weren't shown to the emulators during training. And you can see you get a very good fit all over the globe. One of the things
2 minutes, Duncan.
Okay, I'll speed up a little bit then. One of the things I've glossed over is this distance metric. We, for this work, have used something sometimes referred to as an implausibility metric. So it's essentially just the standardized Cartesian distance between the observations and the emulator output. So we tend to assume that if the observations are more than 3 sigma away from the emulator output, then this is an implausible combination of parameters, and we reject that set of parameters. And so that allows us to build up posterior, as I described earlier. And because we're doing that now with an emulator, we can do that. Actually, ESM does this on the GPU, so it's incredibly quick. We can draw hundreds of thousands of samples a second and draw combinations of parameters that agree with our observations. And so here we see that so red are rejected, green are accepted, and against these observations, we find a slice through this parameter space that agrees with our observations. Okay, and we've used that in a couple of papers already. So this paper from 2020, GRL, looking to constrain one aspect of aerosol forcing, and another paper from Isabel McCoy, same year. I won't go into the details of that, but just to show, where these have been used in practice. Another thing I'm excited about using this tool for is exploring scenario uncertainty, which I mentioned at the start. So interpolating between these, what are supposed to be realistic, but nevertheless, only 5 different scenarios. And so the Climate Bench hackathon event, which some of you may have taken part in, was using emulators to explore generating temperature maps and precipitation maps from different climate forces such as CO2 and different aerosol. And so I'm really excited about the ways that these emulators might be able to help in that space. So I hope I've convinced you that climate model emulation is an important tool for constraining parameter uncertainty. We've been using it for a little while, but it's not commonly known. We've developed a fast and open tool for leveraging these libraries, and I hope makes this whole workflow kind of straightforward. It's all written in Python, it's all open source on GitHub. Feel free to check it out. I'm excited about exploring scenarios, and yeah, I look forward to how it might be extended with different models, and very much welcome feedback and suggestions from the community. So I'll end there and happily take any questions on Slack, I guess.
Indeed, thank you so much.
Thank you.
And yeah, and we have now we have Ziheng Sung on monitoring power plant emissions.
Thank you. Hi everyone. So this is Ziheng Sung from George Mason University, and I'm going to talk about our research progress on how to use AI, and we call that EmissionAI. It's not specifically for one model. We just call a bunch of models, and we try different approaches, and we call that as the EmissionAI to monitoring the power plant from the space. So this is additionally the Microsoft AI for Earth project, and the Microsoft gave us like $15,000 error credit. So appreciate that. We have the data scientists from Microsoft to help us building these models as well. So I'm gonna make it full screen. Yeah, so the background is according to the EPA, the sector of the energy actually contributes the most greenhouse gas emissions across all these sectors of the human society. And the burning of the coal and the natural gas and oil is the largest single source of the emissions. So the IPCC assessment report says, it's no doubt that the human influence has warmed the atmosphere, and widespread and rapid changes in the atmosphere, in the ocean, and the cryosphere and the biosphere has occurred and will occur more frequently. So I think monitoring these emissions is one of our major critical tasks in the next decade. And I think the effective monitoring is a key to control the green gas emissions from the biggest single source. And right now the EPA is regulating the US power plant, which is very good, to report the complete and the continuous observation back on a rolling basis and force the emission on the limit. There is a threshold. So if you emit too much CO2 or SO2 or mercury, and you have to stop. So that forces the companies to use some carbon storage or technique, something like that. But in the cycle, the monitoring is the most critical part, because some companies probably will pursue the profit over the environment's health. So we have to monitor that. But for some other countries, they do not have this such kind of policy in place. So ground or stationary observation probably is not the only way. We do not have that tool to monitor them. So we want to use the remote sensing as an eye in the sky to monitoring all those emissions. So there is no excuse to emit too much greenhouse gases if we found that there is a hotspot there. So this research is try to meet that challenge and use the AI, because the remote sensing, the collection between remote sensing and the single power plant emissions, the collection is quite complicated or sophisticated, because we have no idea if this greenhouse gas came from the power plant or it's from the transportation in the atmosphere. So actually, we are worried at the beginning, because that's absolutely a sophisticated process there, and we're not sure AI can find the patterns and derive the emissions here. And our objective is that we want to use remote sense data to derive the NOx. Actually, we only look at NOx at this point, and we will extend to the CO2 and the SO2 in the future. We want to get the NO2 of any specific power plant at any day of the year, simply using the remote sensing, like the ChopOmi or any other remote sensing data we have. So ground truth data for the training the models, we will use the EPA data. So that's only available in the United States. And I think if the model is trained correctly, it will be generalized to other countries as well. Our methodology is, first of all, the data we used is Sentinel-5 is like ChopOmi data. And we also used some climate variables, like from the remote analysis data and MIRA, including the wind, the temperature, precipitation, the cloud friction. The ground truth data, we use the EPA power grid data, and we collect all the power plants locations using the shapefile from the EPA. We tried a lot of models, machine learning models, the neural networks, including the SVR, random forest, voting ensemble, and the LSTM. Actually, we also tried the convolutional neural network, which normally is used to process images, but we saw that some folks already use it to predict the time series. It's not bad, the results. So we have actually did that, but we found that the results is not as good as the other models. To facilitate our model training, we used some like AutoML technologies, like grid search to make the hyperparameter tuning a little bit easier. And we also do some sensitivity analysis to analyze which variables has the most importance on the results. And we also do batch normalization, which is a normal tool or technology to reduce the errors in the neural network. The computing platform, we used the Microsoft Azure NC6 GPU instances at the beginning and before our credit runs out. We also used the Azure ML Studio, which is AutoML services, and you can just upload the CSV and it will help. It will automate the whole thing, and it will give you the best model it has. The best model they give me is a voting ensemble, but I didn't reproduce that experiment on my own local machine. So at our local machine, LSTM is the best model so far. And we also used the Hopper cluster in GMU and installed the Jupyter Hub to help us to process this data. the results, and we have done certain types of the experiment. Actually, we used only one plant because we think that probably if we fix it as a one plant, all the enforcings will be fixed. So ML model will predict the emission better. And we also use all the plant as a training data set. And we want to say that which model, which scenario the AI will work better. We thought that the one plant will be better, but actually it turns out we are wrong. Actually all plants has better accuracy eventually. And we still trying to figure out why it's like that. I think the big data will help the power plants to recognize all the hidden patterns. Even that pattern doesn't show up on this power plant, but it shows us on other power plants. So it knows that knowledge and it can predict better. And that's our initial guess. So actually the difficult part is some plants has other emission sources nearby, like one power plant is close to other cities, or the factory establishment. Also the agriculture field actually emits the NOT as well. So we choose some testing single site in the rural area, like this one in Arkansas. And we also trained the model on all the power plants, including almost 10,000 power plants across the United States. And we will chef them and train the model. So before we train the model, we do some analysis on the feature importance, and we found that CHOP-OMI absolutely is the most important variable. And surprisingly, the day of the year is the second. So you probably want to include this variable in your training process and make it as important as other variables like the wind, precipitation, or something like that. And one-side comparison, and you can see that this is a scattered point plant. Actually, linear regression is not bad, but it didn't capture the peaks and the valleys. So it's just capture the average value, which is like one straight line. And the random forest compared to the multi-layer perception and the voting sample, random forest is absolutely better in capturing the peaks, but no model did a good job in this region. So the lower, the low emission days is not captured by the AI at all. So we are trying to figure out why it's like this. Maybe it's because the values of the CHOP-OMI always higher than average, but it didn't capture this one. Probably because the wind and some sources and the atmosphere chemistry transportation. So you can see that we mainly look at the MSE, which is a mean square error, and you can see that it's about 0.005, and the MLP actually has 0.04, which is worse than other models. This is for one site, and for all the sites we tested the SVR, so SVM, which is for regression. And we use some configurations here. Use the RBF as a kernel, and the gamma is 0.35%, and epsilon value is 10,000. So this is the result. And actually we got a little bit better results than the one single site. We have 0.003 test accuracy. So this accuracy is calculated on the test data set. It's not on the training data set. Random forest. Yeah, this is a very exciting.
About a minute to go. I'm sorry.
Oh, sorry. Yeah, I think I clicked. So this is random forest, and this is LSTM. LSTM is like it has 0.003, which is the best test accuracy we have. So this is its pattern. You can see that it captures most of the peaks and the valleys, but it's a little bit, there is a little bit delay in that curve. So we are trying to figure out why it's like that, and we want to solve this problem soon. So overall, the MSE divided by the all-plant mean value it means our error rate is about 5%. So that's very impressive. It at least proves that AI can predict emission from the space. And also AI is underestimating the peaks sometimes and also overestimating valleys. And we believe that those problems can be fixed in near future. And we are trying to work hard on that. So this is a summary, and we have all these notebooks available on the GitHub. So feel free to check out and feel free to contact. And that's all I have. Thank you for listening.
And thank you for the talk. And yeah, please encourage all of you to look at the Slack channel. It's definitely going full bore here with many questions, and just about all of the questions answered, actually, as far as I can tell. And yeah, I think officially the session is supposed to close out now. So yeah, I do want to thank you all for attending this. And yeah, once again, please do check the Slack channel. And we also have at 11 a.m. Mountain Time, the plenary session 6, which is the emerging technology for NOAA missions. So yeah, please take any break that you need to, and then rejoin at 11 a.m. Thank you to all the speakers and the attendees, and to Chris Slocum and Lindsay for keeping this session going.